to deal with the education stuff that for that just gosh, just but I think it doesn't.
Right. So, hello everyone. I'm going to be talking about streaming and how we use the Deltalake and Databricks to help us solve a real business problem, which is basically how to do billion row joins in almost real time on streaming data. So, first of all, what is Talroo? We are a programmatic job advertising network, which means we connect job seekers with employers. And we do this through our own website, which is called jobseekcareers.com. But we also have an API that is used by many other people that want to include like a search box for jobs on their website. And we also do other things, but essentially the main point is that we have a massive amount of data coming in. So we deal with billions of queries per month, and we have to use them to train our machine learning models and also do dashboards for customers, for instance, and other users. So the way this works is, if we could, we would like to store all the query metadata with the URLs that we give to our customers. But for multiple reasons, we can't actually do that. So what we end up having to do is to store the metadata for a query separately from what we return to the customer. And what this means is when someone does a query, obviously, that person doesn't always click on the results of the query. So we have a sparse click signal that happens sometimes, and not always. And when a click comes in, we don't have the query metadata present on the click itself, so we have to look back for it. And what does that mean? Well, most clicks happen around 30 seconds after a query. However, there's a very long tail because, for instance, we generate queries through for emails that we send to people. And when you receive an email from like a job site, sometimes the email stays in your inbox for months before you actually click on it. And when you receive a click from you clicking on that email, we have to go back over literally weeks and weeks of data, which might represent billions of queries. So this means we have a stream of clicks coming in. Some of them we have to look back over billions and billions of rows to find the one that actually corresponds to it. So this is basically the same thing as if you had like a bus of people coming into the Library of Congress and looking for a specific page in one of the books of the library. And you want to do this as efficiently as possible and as cost efficiently as possible. So you want to scale, and then you also want to do it quickly because there are uses for your data and you deal with it quickly enough. So the first idea, of course, is divide and conquer. So this is very simple. You just take your data set, you copy it on several machines. Every machine is responsible for a subset of the incoming batch from the clickstream. And then every machine does the join independently. But the problem is this does not actually help solve the problem at the worker level because every worker still has billions and billions of queries. It just has a slightly lesser sub-problem to solve, and it's not sufficient. So what we could have done is we could have had this stream of clicks coming in, and we could have dealt with it via a regular join on a database. So the database could be anything you want. It could be like a key value store, like MongoDB. It could be like a more classic database, like Postgres or MySQL or Redshift. And then we send it downstream for other uses. But what we did instead is we used Deltalake and Databricks streaming to solve this problem. And so in this architecture, you see, you always have a stream because people query all the time our search engine, so we have clicks coming in. We always need a buffer for obvious reasons because sometimes you can't deal with the data as fast as it arrives, so you have to store it somewhere. And also, we deal with massive amounts of data that we want to train models on, so we have to buffer it anyone. Okay. So we need a scalable solution, so that's why we always need something like S3 or the file system. But the thing that we can change is the bottom options. We can do the join on a classical database, or we could do it on something like a Deltalake, which is based on data stacking. So how does a classic join work? Well, I'm not going to go too much into details, but basically a classic join has an index. And what you do is for every query key that you're trying to find, you will go down your index. So your index might be, it might be a hash map or something else. But the most classic example would be like a tree. And at every node of the tree, you're asking the question, am I bigger or smaller than this node? And you either go left or right depending on the answer. If you have n elements, you have log n depth of the tree, and you need to go down that logarithmic depth to find your answer.
I want you to elaborate on the fact. So we were talking about billions of rows of data. Like, how would you have done that before Databricks?
Well, before Databricks, we would have used something like this, like basically a massive Redshift database. But we would have needed to probably partition the data and separate it on multiple machines, each machine doing a part of the join, and some kind of, I don't know, sharding or condition to steal the data. But essentially it's very difficult. And the reason why it's hard is not so much the fact that querying on a classical join is hard, because logarithmic time complexity is not too much, but the problem is, in this tree, you see, let's say you never go on the left of the tree, so you never actually query on data that is 1 month old, or almost never. Well, in the classical case, without Databricks, what we have to do is we have to keep in memory the relationship between these elements that we never visit. So it's like keeping a map with the relationship between all the towns in Russia, or something like that, when you never actually travel to Russia, so you're wasting a lot of RAM. And the problem is when the depth of your tree is too big, when you have too many elements in your index, and it overflows the RAM, that's when you start having bad complexity problems, because you have to flush some of the index into the disk, and then read from the disk, put it in the RAM, and it destroys your performance. So what we do instead is we use Databricks and Deltalake, and we use data skipping, which is a completely new, different way of doing a join. And we enable that using this format, which is the Parquet format, which is extremely simple to understand. Basically, we just divide the data in multiple sublevels. Every level has metadata associated to it that allows us to skip entire files, entire row groups, entire pages to look for the one we need. So how it works, it's as if you were going to like this old, let's say labeled cabinet, and you know that in one cabinet, for instance, the minimum value for the query key is A, the maximum is C, and your query key starts with a D, so you know you don't even need to open that file, so you save time on that. And you have this at multiple levels, at the file level, at the row group level, and at the page level, correctly. So this allows you to ignore most of your data. One problem you can have with this approach is if the min and max values are not informative. What this means is, imagine if your query key is random. If it's a random hash you compute, then none of this works. The reason is because it would be the same thing as if you were entering the Library of Congress and every shelf was labeled A to Z. Essentially, the data skipping only works if the key that you're doing the join on is monotonically increasing or decreasing key, which allows you to skip most of the files. And this is, if you want to go deeper in the analogy with the library, the way you actually look for a book in the library is not for an index. It's more akin to data skipping. So you start by looking in, let's say, the fiction section. Then you look for the authors that start with A. Then you look for your specific author. Then you look for your book. So it's very similar to what actually happens under the hood in Databricks. And yeah, that's what and also there's a additional interesting point, which is that you don't actually load in the metadata for the files that you're skipping. So the upper level metadata has to be stored in a centralized place, of course, but the lower level ones, for the row groups and the pages, you don't even actually look at them if you skip them. So this is the same as if you're looking for a book in the fiction section, then you don't care about how the non-fiction books are ordered between one another. So this is what basically Databricks is doing by skipping the metadata for the files that you're skipping. So what are the pros and cons? The pros that the data at rest is on a file system. It's not on a machine. Whereas on every other regular method that I talked about earlier, MongoDB, Postgres, SQL, you need to have a computer running for your index to be existing. So this means that it's very expensive because you have to pay for the RAM of your computer. If you have, let's say, your traffic and flow between 10x and 1x, very quickly you have to over-provision and you waste a lot of money. So that's a pro of data skipping, that your data at rest is on a file system and you only provision machines if you need them. Also, the fact that it's on a data system means it's a lot easier to parallelize, and because you can just copy it over to a different machine, the data and the index are basically the same thing. So when you're copying the data, you're also copying the index. And obviously it's more scalable because you're not loading in memory the relationship between elements that you're skipping. The cons are that if you're not doing it right, you might have to open lots of useless files. Another con is that because it's a columnar data format, it means that the information of every different column is stored in a different page. So if you're loading in 100 different columns, you have to open 100 pages instead of opening a single page that contains the entire row on a regular SQL database. So it might be slower in some cases. And generally, for small data sets, like you have just a few million rows, it's probably better to do Postgres and to do just a regular join than to do the Databricks streaming solution. Yeah, and the result is that we were able to use this architecture, this technique, to process billions of queries almost in real time, so 20 or 30 seconds, which allows us a lot of possibilities downstream, because when you deal with data this quickly, then suddenly you can use it for the next click that the user is doing, or you can use it for other purposes like bidding, etc., etc. There's lots of uses of your data that are time sensitive. And finally, another advantage of this is that it's very easy to scale in numbers of workers. So essentially nowadays, if we have 100 times the traffic tomorrow, the only thing we need to do is we need to tell Spark to delegate to 100 more workers. But otherwise, the rest of the architecture will remain the same, which would not be the case if we were relying on regular indexing. So that's it.
Any questions? Any questions from anyone?
I would have a question. I'm sorry. So first off, you said a couple of things that are intriguing. Well, question number one. Question number one is, well, I want to make an observation. Number one, you said billions of rows, which clearly you had no reaction to, as I'm saying, billions of rows. But billions of rows is a lot of rows for most companies. So I'm curious, from a scalability perspective, like what did you do before Databricks, and you circled around it? Would you have attacked this problem? That's question number one. Question number two is around what your under the radar Databricks feature. What's your under the radar Databricks / Spark feature that you think people need to take advantage of that maybe is under the radar?
Okay, so if we did not have Databricks, the way we would have done it is we would probably just have given up on the problem and instead we'd already have the data from the URL. Because it's just too hard. But the problem of putting everything in the URL is that all the people that are using Internet Explorer, they can't actually load your page because Internet Explorer sucks. So that's one problem. And the other problem is some like search engines, they won't actually even crawl your page if the URL is too long. So that's the problem of putting stuff in the database. And I think maybe an underrated feature that we use quite a lot is the ability to, it's like a very niche and specific streaming function where you can say, oh, just limit the stream to batches of 2 gigabytes. So we use that and it simplifies our code a lot because before we used to do like an initial stream where we had different parameters and then an incremental stream, but with this new feature, we simplified a lot our code base. So, yeah.
Any other questions from anyone? Don't be shy. You got plenty of sake in you.
All right, let's give a round of applause to Adrian. I think the key takeaway for me there was they would have given up on the problem if they weren't using Databricks. All right, so now to the next phase of the program.